And in this talk, we have Professor Richard Kueng from Linz University at Austria. So he's originally from Linz, from what I understood. And he did his undergraduate at ETH Zurich in, at ETH. And he did his PhD in Cologne and postdoc in Caltech, and now he's professor at the University of Linz at the Computer Science Department. And he will talk about classical shadows of quantum states. Please go ahead.
Yeah, thank you, Sari, for the introduction. Hi, everybody. I'm Richard from Austria, and thank you all for being here. This is an amazing, huge conference, but I don't know about you, but I also find it's very, very dense. There's a lot of talks and a lot of places to put attention to. So thank you all for coming here and choosing to maybe pay attention to my talk. It means a lot because I think we are a bit of outsiders here. It's not we are in a computer science department. We do quantum computing and we care about scalability, really getting the most out of existing quantum simulators and maybe near future devices. And this is also the topic of this talk and the reason why we got the Frontiers of Science Award. So here's a brief outline. I want to first start with the motivation about the big questions that keep us going. They're still very much inspired by physics, but maybe you can also see why computer science starts to play a role here. Then I want to introduce the star of the show, classical shadows, a new data format for dealing with quantum states. And then, if time permits, I want to also talk about two possible applications. One of them is synergies between quantum experiments and artificial intelligence. I think this fits nicely to the overall scope of this workshop. And the other one is maybe a bit more speculative and visionary. It's all about new types of quantum advantages. So unlock new potential of quantum computers. But let's see if I get there, because I encourage each and every one of you to ask questions whenever there's something that you don't fully understand. In my experience, if you have a question, at least 5 to 10 people in the audience have the same question, and please interrupt me and give me the chance to clarify. I'd rather have it that you understand the main things and help me to convey the main ideas rather than rushing through all my slides. Okay? So comments and questions are very welcome throughout all stages of the talk. So before I want to start in earnest, I want to give credit where credit is due. This work is based on collaborative work with two amazing researchers, Robert Kueng, who when I was at Caltech only started as a PhD student, and we quickly started to collaborate on ideas that ultimately led to this classical shadow framework. I think he now got appointed assistant professor at Caltech directly after the PhD, which is very, very commendable. And John Preskill, I guess he needs no introduction. He was the lead of IQM when we were there, and he also played a huge role in thinking about possible applications of our framework. So this is really collaborative work, and the praise should also go to them. So here is now really the motivation, what keeps me going, and maybe also explains why I ended up in a computer science department. I'm very excited about these decades or years when you think about quantum computing and quantum information processing. Because since 2019 or so, for the first time ever, we have been access to these wonderful quantum machines that can host hundreds of qubits these days. I mean, they are not perfect, they are noisy, they're intermediate scale, but we have they host hundreds, maybe thousands of qubits, and they allow us to do at least short time calculations in a noisy environment. But this is something we simply didn't have when I was an undergrad student. And for the first time ever, this scaling starts to matter, because if we have systems comprised of hundreds of qubits and we do quantum computations or quantum simulations, then the information that is interesting for us is not readily available in a human or machine readable form. Usually the things we care about are hidden within quantum correlations or entanglement of the qubits themselves. And so in order to access them, we have to measure the system, right? This is just how we access information in the quantum realm. And these quantum measurements are destructive. So they destroy the system. And so in order to get a new data shot, we have to redo the entire quantum computation again. And then we get a second shot, and then we can start doing that over and over again, and maybe average to get access to the correlations we have. Right? So far, so easy. This has been known for hundreds of years. And if we kind of like think a bit into the future, then we could also kind of like think about a classical computer that processes this data. Because if we have more and more qubits, the measurement outcomes become more and more involved, and we shouldn't compute everything by hand. We should use a computer for that. So we now have actually kind of like two types of computing platforms, a quantum device, or a QPU, and a classical device, or a CPU. And the two should work together. But in the intermediate regime, we have this readout problem, that the quantum information is stored within correlations of qubits, and the normal computer only works with bits. And so we have to solve this readout problem. And if we are not careful, then we get additional complexity parameters in the readout stage that can scale exponentially in the number of qubits. If we just do like kind of like what we do as the textbook says. And this is a problem because if we have 100 qubits, exponentially in 100 qubits is 10 to the 30. And no supercomputer in the world can handle this. And it would mean that we would have to repeat the quantum simulation or quantum experiments 10 to the 30 times. Lifetime of the universe isn't fast enough for that. So we really need new ideas on how to extract the relevant and meaningful information out of these quantum systems. And I would argue, importantly, we need scalable ways of doing so that the number of repetitions we need, the number of shots we need, doesn't grow exponentially or very, very poorly with the number of qubits. Because unless we don't solve this problem, the quantum computers become too big to be used by us. And so this is really a fundamental challenge. And this readout problem is really what keeps me, my team, and our colleagues going. And what we envision is kind of like a bridge, a new way on how to extract this relevant quantum information directly from the quantum realm and map it onto classical data structures that can be efficiently processed. And what we do, and I think this is rather new, is we consider a unified treatment of all computational resources. Like when I did my undergrad, let's say 15 years ago, people either only focused on minimizing quantum resources or classical resources, but never both. And so we really strive to take into account, we are willing to invest a short quantum algorithm, which might be expensive because kind of like everything is noisy, if it gives us a huge benefit in classical compute time or memory. Okay? But really try to keep them both on equal footing and try to get the best of both worlds. And we want to do this in a way that we use quantum theory or quantum mechanics itself to help us, kind of like find new solutions to this dealing quantum problem by using quantum solutions. And we want to have this kind of like in a nice format that allows us to learn something from the data very quickly. So not kind of like a useless data structure, but something that I can really use to input in a machine learning model, for example, to use machine learning and artificial intelligence to help analyze the data as well. And I want this now and not in 10 years. So we also care about implementation. So no hard, very, very deep quantum algorithms, but something that we can do now. Okay? And if we meet all these three desiderata, I would argue that we actually get a bridge between the quantum and the classical realm. And if we do this carefully, and I will show you how this is possible, you get a bridge that is universal, parallelizable, and scalable. And so just to paraphrase it in a very naive term, we are looking for wires that allow us to wire a quantum computer into a classical computer with as little overhead as possible to use the whole thing synergetically. Are there questions or comments at this point? I don't see anything. This is either very good or very good. I choose to believe that this is very, very, very good. So let me briefly tell you, or kind of like now tell you what our approach was to solve this quantum readout problem. And in order to do it, I think it's good to go back on how we learn in our undergrad courses how quantum measurements work, right? And I learned in my quantum mechanics class that a quantum device, kind of like a quantum computer, produces a quantum state. characterized by a density matrix. And then the measurable properties are quantum mechanical observables, which correspond to Hermitian matrices. Exactly. And the expectation value is the trace of this observable with the density matrix. And if you now want to measure a certain observable, you do an eigenvalue decomposition of this observable in order to get the unitary that transforms into this eigenbasis. You apply the unitary as a quantum mechanical evolution to the density matrix to rotate into the eigenbasis of the Hermitian observable, and then you start the measurement. Okay? But if you think about this, now think about you're interested in, let's say, not one observable, but 10,000. Then what would you do? You would start with the first observable, diagonalize it. This gives you a quantum evolution. You would apply it to the quantum state, right? Then you get a shot. You get a single shot. You want an expectation value. You have to repeat this many, many times to get enough statistics. Then you move on to the second observable, do the same. Move on to the third, do the same, right? So if you think about it, this process, this textbook process, is special purpose in the sense that we need a different unitary transformation for each observable, and it's sequential. If I want to learn 10,000 observables, I might have to measure 10,000 different kind of like evolutions, unless there's advantageous structure, right? And maybe you can see that this can quickly become a bottleneck. And so what did we do? Kind of like Robert, John, and myself back at Caltech, let's say roughly 5 years ago, we proposed to do something else, which looks maybe crazy on first sight. We proposed to replace this specific unitary rotation that is observable dependent by a randomly selected unitary. Think about sampling from the GU, from the uniform measure of all unitaries. You sample a unitary, then you apply this randomized unitary to your quantum state, and then you do a single shot measurement, and you get the outcome, a classical bit string. And then you do that again with a different randomly sampled unitary. And then again, you get a bit string as an outcome. And then you keep doing this and doing this and doing this. So we completely ignore the actual observables and do a random unitary transformation instead. Why is this not completely crazy? Well, because of group averaging. If you think about at each time I take a data shot, I do a random rotation, and then I take kind of like a measurement. And this tells me that on average, I see the outcomes of all possible rotations, right? And this also tells me that on average, I see signatures of the full density matrix in all possible directions, because this is how I sample the unitaries, right? And so on average, in expectation, I get complete information about the entire density matrix. And having the correct expectation opens the door for Monte Carlo approximations, for approximating these idealized expectation values with finitely many samples, right? And this is what we do in classical shadows. And these Monte Carlo approximations that you can do with the data, they can now be parallelized. If I have 10,000 observables, I take these randomized snapshots, and I can use each snapshot in 10,000 different Monte Carlo approximations of the 10,000 observables at the same time. Okay? And because on average we see everything, this procedure is also universal in the sense that it allows us to reproduce every observable. The question now only is, how long does it take in order to get enough statistical data for Monte Carlo to converge? Okay? This is the overall idea. And what we realized is that the time it needs to converge for many different observables is much quicker than you would think. And you get huge improvements with such a strategy. Okay? Let me now go a bit more into details how we actually do that. Yes? Yes. Well, thank you. Thank you for staying with me. Yes? Yes, I will have a movie later, okay? Thank you. So kind of like here's how we concretely interpret that, because the way I described it, I was emphasizing kind of like a generic big unitary from the uniform ensemble, right? This is not tractable. So I have to actually do a random unitary that I can implement on a quantum machine. So it shouldn't be a generic unitary, but maybe something that has locality. And this is also something we do in classical shadows. And now envision really a system where you have n spins or n qubits. And then the way we do it is every qubit, every spin has 3 natural basis directions. Spin across the z-axis, x and y-axis. These are 3 different basis choices for each qubit. And in order to generate our randomized sketches, we just alternate randomly between these 3 basis choices for each of the qubits. Note that there are exponentially many, namely 3 to the n different basis choices for the entire ensemble. But each time I just choose one of them uniformly at random. And this is very efficient because the transformations are single qubits. They only ever affect a single spin. Okay, so this is what you see on the left-hand side. It's not a big unitary that affects all the qubits. It's really a Kronecker product of single qubit unitaries. And this is something all existing quantum architectures can do. And then we just record the outcome, which is now in an n-qubit system, a bit string of size n, where each bit tells us whether the spin we measured was up or down. And so this is what we store, together with the information about what random unitaries we did here. But this is really now in the level of bit strings. And if I have 1,000 qubits, I get a bit string of length 1,000. And another kind of like sketch that tells me which 1,000 rotations did I do. So this is scalable. I hope you can see that as a classical data structure. And this outcome, the outcome state, is now actually a bit string of outcomes, up or down, what did I see? And a string that tells me which basis did I measure in. Was it X, Y, or Z? But I can do that together. And what we showed, using group theory actually, is that we can use these bit strings to construct an approximation of the full density matrix that is just an elementary Kronecker product of individual single qubit terms. Basically, we measure and kind of like we destroy all the entanglement in the measurement. And so this is the post-measurement states. And so there's no correlations. And so it's an actual tensor product. And so this is a scalable sketch that I can scale up. And we can use group theory to show that we actually get the exact kind of like a sketch that exactly reproduces the underlying density matrix in expectation if we kind of like invert a depolarizing channel. So what you see is actually an unphysical, randomly constructed tensor product of n single qubit density matrices that exactly reproduces the underlying density matrix in expectation, no matter what the underlying density matrix is. Okay, this is what I kind of like alluded to in the last slide, that if we randomize our measurements, we can see all corners and we can get a sketch, a Monte Carlo approximation of the density matrix that is faithful in the sense that it reproduces all possible density matrices. Okay, yes? Yes. The question is how much data do I need? This is kind of like each time, this is now a random matrix. For each experiment, I get a random matrix. I get a single shot. And the question now is how many shots do I need in order to learn an observable? It's not kind of like, this is not a big question. And for generic observables, it's going to be exponentially many shots. And so this doesn't violate the fact that with n qubits, you have exponential degrees of freedom. But some observables are much easier, and then you can recover them quicker. Yes, exactly. This is why I won the prize. And when you then just do classical statistics, we're now in the realm of classical statistics, we can ask ourselves, if you give me an observable, I can actually use classical statistics to compute an upper bound on the number of shots that are necessary to recover this particular observable to a desired accuracy. And I think I wrote it here. The number of measurements you need in this setup to reproduce an observable scales exponentially, but not in the number of qubits, but in the locality of the observable. So for example, if you have a local observable, like a two-body correlator, this thing will converge very, very quickly. Yes? Okay. This here Thank you. This is a random matrix because it is constructed from a quantum experiment that had a randomized outcome. So this is like an important sampled random matrix. And we can compute the expectation value. Yes, yes. And we can show that if I take the expectation value over these probabilities, which depend on the true quantum state, it will reproduce the actual quantum state. So this is correctness in expectation. And this is a bit like Monte Carlo for big data, where we take huge matrices and try to write it as a probabilistic average of simple matrices, and then we start empirical averaging. This is exactly the same thing. But the important sampling part, the hard part from Monte Carlo for big data, is done natively on a quantum computer. Okay? And now what I'm saying is we have n qubits, and so there's additional structure. And the marginals start to matter, because if I care about an observable that only addresses qubit 1 or 2, which is, for example, a correlator, qubit 3 to 1,000 don't matter. And so I can just marginalize and trace out. And because this is an elementary Kronecker product, marginalization is easy. And so I can just look at the subspace I care about, and there the dimensionality is not 2 to the 1,000, but 2 to the 2. And then it's reasonable to think that in this marginal space, convergence happens at the scale of the dimension of the subspace, right? Which is now only exponential in the number of qubits that survive. And this is exactly what I wrote down here. This is just using Höfting's inequality or Bernstein inequality for convergence of random variables. Okay? Did this help? Thank you. I'm sure it helped more people. And now maybe I can come back to your point. If you're now thinking about an observable that is just correlated between qubit 1 and 2, the number of shots I need is 4 to the 2 is 16 over the desired accuracy squared. And this is just shot noise or the curse of Monte Carlo. Because we have a sampling problem, kind of like the error only decays with 1 over epsilon squared. It's just central limit. The desired accuracy you want for your observable. Like you tell me the observable and the error bars. And epsilon is the size of the error. And then the one surprising thing that was also mentioned quickly in the kind of like award ceremony is that if you're now interested not in one observable, but in many of them in L, then the number of shots you need to get all of them correctly only scales logarithmically in L. And this is just probability theory, because I have kind of like, if I have L different estimators and they concentrate quickly, then how many samples do I need to get all of them? It's log L times 1. This is basically the coupon collector argument. And so if we now think about a 1,000 qubit system where you might be interested in all two-body correlators, then there's roughly 1,000 squared many two-body correlators, right? That's kind of like 10 to the 6, it's a million, but all of them are two-body. And so how many shots do you need? Well, it's 4 to the 2 is 16 times the logarithm of a million, which is 6. Okay? And so you can really kind of like predict many of these observables jointly in parallel. And I think sometimes a movie says more than 1,000 words. And so I actually prepared a small movie that illustrates this. So this movie is now a simulation of this classical shadow estimation technique for a small system comprised of 4 qubits. And I now press play. And you should really think about the quantum computer doing work in the background. It prepares the state, we do a randomized measurement, and it prepares it again. And each randomized measurement produces one point here. And I could either try to approximate the full density matrix statistically, which will take a lot of shots because it's a big object, or I could directly look at the observables. And here you can see, for example, all possible 2-qubit correlators that are in the X spaces for all possible subsystems of size 2. I could also look at all possible two-body correlators in the Z direction for subsystems kind of like, and here you can see there's 4 qubits, so there's 4 different options. I could also look at nonlinear properties like the purity and use this Monte Carlo technique to estimate nonlinear functions, which you can see here. And I hope what this conveys is that all these plots independently converge very, very quickly. And they converge much, much quicker than the full density matrix description here. Okay. And you can do all of that in parallel. And now actually everything has converged. And we can already see what kind of 2-qubit quantum state we have. because here the blue plot here tells us the purity of the system, which is 1. So we're dealing with a 4-qubit pure state. Here you can also see the reduced kind of like purities for reduced subsystems of size 2 again. And one of them, the orange one, is 1. So it's pure across 1 bipartition. And the others are maximally mixed. And so what this tells you is that the 4-qubit system actually has to be the tensor product of 2 maximally entangled states. You can see that here already. And if you also look at the 2-qubit correlators here and here, you can see that you can infer that this is the Kronecker product of 2 belt states. A maximally entangled belt state between qubit 1 and 2, and another maximally entangled belt state between qubit 3. And all while kind of like this full density matrix has still a very, very poor convergence in the sense that the density matrix approximation has many negative eigenvalues. And I now kind of like zoom ahead. It would take much, much longer for this histogram of the density matrix to be sufficiently denoised for you to see that it is really a Kronecker product of 2 belt states. Okay? And this is really what we had in mind. Kind of like a machine where the quantum computer takes data and we, in a streaming online fashion, use Monte Carlo approximation to already process the data while it's coming in and predict everything we want. Is there questions or comments at this point? Yes. Yes. And let me answer that. This is a very good question. One thing that you can show, which is actually a very desirable feature, is that in each shot, we randomly choose an X, Y, or Z basis. So suppose that you have a measurement noise. Then this randomization actually averages out the measurement noise and turns it into a depolarizing channel because you randomly kind of like use different bases. Okay, this is kind of like spam twirling, or this is like a known techniques in quantum computing to combat noise. And now I just very quickly get technical. The depolarizing channel also features here. So if I kind of like I can do a calibration stage where I just kind of like take a known state and compute known observables to get the depolarizing rates associated with my measurement error, and I can counteract it here. So there's a built-in error mitigation strategy that actually allows you to deal with measurement noise. So I think this is a very, very good part here. What I can't deal with, and I don't want to deal with, is noise throughout the quantum computation, because I actually maybe want to learn this noise. So kind of like just whatever density matrix you get, the actual measurement procedure here can be error mitigated with a very, very simple and rigorous technique. Does this answer your question? Is there more questions or comments? If this is not the case, I would move on to applications. And one application that was kind of big when we came up with this idea were these variational quantum eigensolvers or variational quantum algorithms that you use in order to prepare interesting quantum states on a quantum computer. And one model that we really liked, and it actually has something to do with quantum electrodynamics, I think, is the group around Peter Zoller and Rainer Blatt devised a variational quantum algorithm to find low excited state of a lattice-Schwinger model in 1 dimension. And kind of like the twist that they did, and I think this is very beautiful, is they didn't minimize the Hamiltonian, which would only give you the ground state, but they minimized the variance of the Hamiltonian, which vanishes around eigenstates. And this allowed them to also prepare or find the first excited state, for example. But if you measure the variance of the Hamiltonian, it's a square, right? And you get many more terms. And if there was advantageous structure before, it gets lost because you kind of like have to combine all the possible terms. And this was actually a problem for them because their quantum computer, in their quantum computer, they could have gone to 20 qubits or more. But because there were so many terms in the Hamiltonian, each step in the variational quantum algorithm was so expensive for them that they could never push it beyond 7 qubits. Okay, and this is what you can see here. If you increase the system size, then the cost of approximating your current variance of the Hamiltonian also grows polynomially, right? More terms, more qubits, more terms, square, even more terms. And kind of like, if you do this naively, it would look like this. It would kind of like scale like n to the fourth. Now the team around Peter Zoller worked very hard and looked at these Hamiltonians and found this blue curve of a smarter measurement of many terms by using commutation relation. So this was really kind of like an impressive improvement, which allowed them to push to 7. Our technique, randomization, not think about the problem at all, is the red line. This is basically the theorem you saw on the last slide. Because for us, we use Monte Carlo ideas and parallel estimation, so the number of terms only enters logarithmically. So n to the 4 is just 4 times log n. And if you actually look at it a bit more closely and use some standard computer science tricks for de-randomization, you get the orange line. So this, at least kind of like over the last 5 years, this really could make a difference, especially when it comes to like analyzing not completely standard variational quantum algorithms. Is there questions or comments at this point? Doesn't seem to be the case, either very good or very bad. Then let me move on to kind of like the last part of the talk. So I now told you about what classical shadows are and how we can use them to really make estimation of properties that a quantum computer or a quantum experiment provide us much more efficiently. But I'd argue that these classical shadows can do more, especially when you think about synergies with artificial intelligence and machine learning. And so one example that we looked at is very famous, the ground state problem in quantum many-body physics. It's, I think, one of my favorite problems. It's a big problem in the field. And I think it's beautiful because what is it? It's kind of like the input to this problem is a Hamiltonian structure, in this case, a hexagonal lattice. And for each of the couplings, you can see in blue here, you get a coupling strength and a two-body Hamiltonian, right? And so if I have n qubits, the description of the problem is typically linear in n, right? Because we have a lattice, and so we don't have all-to-all connections, and so kind of like the number of connections in a lattice is linear in the number of elements in my lattice. This means that we can efficiently store big classical descriptions of very big Hamiltonians. Million qubits, no problem. I just have to store a couple of million coupling parameters. Okay? And now the ground state problem asks for finding the quantum mechanical ground state of this system. And this is a completely different beast, right? Because n qubits means 2 to the n amplitudes in a pure state. This grows exponentially. And so already kind of like moderate sized systems can give us ground states that are hard to get and arguably, it's very important, also hard to store. So this problem is not completely well posed. If I want to find an efficient algorithm, I should make sure that the input scales efficiently in n, and the output should also scale efficiently in n, right? And asking for a classical representation of the ground state doesn't do that. Because how would you provide the answer? By writing down all 2 to the n amplitudes? Well, this cannot be the answer. So what we also have to insist to make this problem well posed is to look for an efficient classical representation of the ground states or properties of the ground state. Not the full state vector, but maybe the magnetization, maybe two-body correlators, maybe things that also scale in system size. Okay? And if we have this, we have a well-posed problem. Input, classical description of Hamiltonian. Output, physical property like magnetization or two-body correlation. Okay? Now we can ask, how can we get from left to right? And the traditional method, like one of the traditional methods, is direct computation. And this is exponentially expensive. Not because the problem is hard per se, but the dimensionality explodes. We have n qubits, the Hamiltonian is a 2 to the n by 2 to the n. Note that there are smart techniques that sometimes can solve this. Like think about DMRG, but it only works for certain classes of Hamiltonians, right? Not universally. And what do we do with problems where DMRG, for example, is non-efficient? And here, arguably, machine learning could help. You could try, instead of a direct computation that goes from left to right, you could adopt a learning framework where you assume that you don't have to solve the problem from scratch, but maybe you have access to training data, to let's say 10,000 similar Hamiltonians and the associated ground states. And then you can start training a neural network on this training data to give you a direct connection from input to output based on data, right? This is what machine learning is all about. And arguably, this would be an improvement, because if I have this hexagonal lattice family, I can maybe invest computer time to brute force search, solve it 10,000 times for random configurations, and then I can train an efficient classical algorithm that allows me to answer the problem for new configurations. This is what machine learning is all about. And so the question is now, what kind of data, how should we present the data, the training data, to this machine learning algorithm, right? And what we proposed here is that as input to our machine learning algorithm, we take a randomly selected coupling configuration to uniformly sample over all possible couplings associated with this particular lattice geometry. And we need a classical description of a quantum state, a classical description of the ground state of the associated object. This is the label associated with this. And if we are not careful, the full density matrix is exponentially expensive, right? It's a 2 to the n by 2 to the n matrix. If I use this, I'm screwed, because just reading the training data takes exponentially long. So we need a clever data form. And what people traditionally used is tensor networks, because tensor networks can give you a compressed representation of quantum states. There's just two problems. Tensor networks are not correct for every possible state. And if you want to analyze this, there are nonlinear embeddings. A tensor network, this is a technical comment now, decomposes a pure state vector into a product of matrices. This is highly nonlinear, especially if I want to lift it to the setting of density matrices. If I take one MPS density matrix and add another MPS density matrix, I don't get an MPS density matrix. Okay, so the internal geometry is very complicated, okay, which makes the analysis difficult. What we proposed is to not use tensor networks, but use classical shadows of quantum states, because this is also can be viewed as a classical data format that stores information about a quantum state, right? This is the whole thing. And classical shadows work for every state. They might not work efficiently for every observable. I might not be able to reproduce every observable efficiently, but they work for every state. So in contrast to tensor networks, which approximate every observable but might not work for every state, classical shadows work for every state, but not necessarily for all observables. So we can use classical shadows in regions where we know that tensor networks don't work, like in 2D systems. And long story short, this works. On the top right, you can see a numerical example of a 2D antiferromagnetic Heisenberg model. This is not easy to do with MPS. There's 25 spins. We randomly selected the couplings. And here you can see one randomly selected configuration and the two-body correlations of the individual spins listed, labeled from 1 to 25. So these are the the ground state correlations of this particular random 2D Ising model. We computed this by having a co-author at Amazon Web Services who fried their cloud computing time. On the right-hand side, you can see something that looks very similar, but it's the result from our machine learning algorithm, where we did not do that, but generated 10,000 training examples using supercomputing time, and then trained a classical machine learning model to directly take the new input configuration and map it to the two-dimensional correlation matrix. And you can see that the two, you probably can't see it because it's very small, but the two are very close. And what made us proud is this is not only numerics. We could use the features of classical shadows to equip this idea with a rigorous theorem that states that under strong physical assumptions, this entire pipeline provably works with polynomial resources throughout. And the strong physical assumption is essentially a constant lower bound on a spectral gap, so deep within a phase. It's your ensemble of Hamiltonians has a constant spectral gap, then you can really train a machine learning model to do that efficiently. It's essential to use classical shadows, and the number of training data points you need actually only scales polynomially in the number of qubits, and in subsequent work, we mentioned to improve this to polylogarithmically and even constant. Okay? And here, yes? Yes. Why? Okay, we choose a lattice configuration like this, and then we choose our couplings randomly and compute the associated ground states. The ground states are not randomly selected. They are ground states of a randomly selected Hamiltonian, but the configuration is the same. So this is not a generic distribution. That for kind of like here, I choose one, have one phonic configuration and have to choose the coupling parameters at random. So that I am in this kind of like machine learning setting where I can prove stuff, where I kind of like sample from one known distribution training data, and then I sample, then I train, and then I evaluate the quality of my machine learning model on a test instance that I sample from the same distribution. Okay? And the distribution we choose is a random distribution of couplings for a given lattice model. It doesn't have to be the uniform distribution, but it has to be fixed. And this is now kind of like random on the level of couplings, but not on the level of physics. Because kind of like the geometry is still the same, right? And so kind of like the ground states will be very correlated. And so this is what we actually use as labels. And this allows us to actually forward the information. Was this helpful? Thanks. Yes. Very good, because I'm scared of deep learning. Kind of like what I would use here is ideally a deep neural network that takes inputs to outputs, but we wanted to prove something. And math of deep learning is very, very hard. And the neural tangent kernel arises if the number of inner layers in a neural network is asymptotically large when compared to the parameters. And something beautiful happens there. You can prove that the trained machine learning model acts like a linear interpolation kernel. Okay? So mathematically speaking, in the neural tangent regime, what a machine learning model does, it does linear interpolation of the training state. In this particular case, the ground state approximation of the new ground state will be a linear combination of the ground state approximations of the training data. Okay? Yes, yes, yes. We're using it for a proof. Yes. And thank you for asking this, because neural tangent kernel, mathematically speaking, is a linear interpolation. And so you want to have a data structure for your density matrices that is also linear. Okay, because you want that kind of like a linear combination of density matrix representations is again a density matrix representation. And tensor networks don't have this feature. Because if they are kind of like a linear combination of tensor networks, is not a tensor network. Yes. Yes. Yes, exactly. Yes. But the trainable parameters is a classical representation of the density matrix here. Okay, just believe me. And then you get a linear combination. And for MPS, I can't use this analysis for proof, because if I add two MPS up, it's not an MPS. What we use. Yes. 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 Yeah. Yes. Well, because here we kind of like use the linearity in the density matrix, and the non-linearity happens by going from input parameters to the ground state. Kind of like input parameters to the ground state, that is our label, and then the neural tangent kernel is linear in the ground states we use, that's the one that we use. And then you can really think about linear interpolation and use the fact that the classical shadows I described are Monte Carlo technique, and so they are linear, whereas existing data structures like tensor networks are not. And this allowed us to prove things. Yes, exactly. And the features are classical representation, a classical shadow of a quantum state. And what this machine learning model does, it takes classical shadows of trained ground states and interpolates it to obtain a classical shadow of a ground state you haven't seen yet. And it does so provably efficient and correct. Thank you. Yes? Yes. No. In a 2D system, I can have a constant spectral gap, like in this antiferromagnetic Heisenberg model, and the tensor network approach doesn't work because you would have to use PEPs, and the contraction is not efficient. Yes. 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 Excellent question. Like PEPs works, but you can't contract PEPs efficiently. Yes. Excellent question. Excellent question. I could. I now have like two options. The options that we chose here is to use a classical computer to brute force the ground states and then simulate the quantum experiments on these ground states, which can be done efficiently in order to generate the classical shadow. But we could also outsource this to a quantum computer and compute the classical shadows on the quantum computer. But what we don't make is any statement about how to get the ground states. And this is a general feature of machine learning. I'm oversimplifying here, but I'm not surprised anymore that machine learning models can learn to solve hard tasks, because if you actually look at a hard task, getting the training data is also hard. So kind of like we want to solve a hard problem, like the ground state problem, and the hardness cannot disappear. And so we basically push the hardness to the question of how to generate the training data. But we have the option of either using classical cloud computers, kind of like supercomputers, or a quantum algorithm. This is a new possibility. Yes, yes, I agree. And we don't make a statement about how to get that, and it's probably a hard problem. But arguably, this was also not the point here. We just wanted to show that you can generalize and you can kind of like learn from relatively few training data to extrapolate to many new situations. And just very quickly, you can do something similar if you want to kind of like learn to distinguish exotic quantum states. Like we have a similar storyline where you can do binary classification of trivial phases or topologically protected quantum phases, where we actually kind of like use these classical shadows and develop a new type of kernel function called a shadow kernel, which plays nicely with the classical shadows, which essentially linearizes the topological quantum relative entropy by Alexei and John. And this actually allows you to prove that binary classification also works for these exotic quantum phases, where you can now, again, you assume that you get a test sample from either a trivial phase or a toric code ground state phase. And the question is, which phase does it belong to? Binary classification. And it also works, with provable guarantees using similarities. And then I actually want to go to the end because we had a lot of lively discussions already. One thing I now don't want to go into detail is looking at this classical shadow framework allowed us to unlock new applications, new synergies with learning, but we also found it inspiring to look at classical shadows and see where they fail. Because sometimes in my experience, if like a method fails, it's either because the method is stupid or there's a deep reason for it. And we did that kind of like for these classical shadows. And just as a reminder, these classical shadows work well for estimating marginal properties or subsystem properties, but they struggle with global properties. If I have like a very complicated global question, like a global fidelity with a very complicated state, I will need exponentially many samples to get good accuracy. And I think this is a question you had asked earlier. And now you can ask yourself, is this a fundamental feature or is this just classical shadows being bad? And together with the team at Google, we looked at this and we actually found new separations in quantum statistical learning theory. So kind of like as a summary, the problem for these global observables, why are they expensive for classical shadows, is not the classical shadow technique, but the way we think about quantum measurements. So kind of like, I don't want to go through the proofs, but what can happen, and it happens here, is that usually when we think about a quantum measurement, we think about let's prepare the density matrix, let's do a unitary transformation, and then let's measure. And then we get one data. And then we do it again. We prepare the density matrix, we do maybe a different unitary rotation, get data, and we do it again, right? In information theory, this is called a sequential measurement procedure. We prepare the quantum states one at a time, we measure, and then we predict. And in classical statistics, this is the best you can do. But in quantum, it's not, because there's entanglement. You could also envision a procedure where I prepare my density matrix once, I prepare it again twice, and then I store it in parallel in a quantum memory. Now I have 2 copies on twice as many qubits. And now I could do an entangling measurement on the 2 copies. And this cannot be captured by classical statistics. And this could really be empowering. And what we basically showed with some 2 examples is there's cases where this prepare and measure scenario that has been done, I think, since quantum mechanics was invented, and also which classical shadows use, is provably exponentially expensive, just by the way the data is acquired, but with a loophole that if I had access to pairs of copies at the same time, I could quickly learn it. And a cool example is what's called purity testing. This is kind of like a 2-outcome possibility. We now play a game, me against you, and I do one of 2 things, and you have to guess which one it is. I either hand you the maximally mixed state on n qubits, uniform garbage, or I hand you a pure state, but a pure state that is randomly selected from all possible pure states. Yes? Oh, thank you. Then this is very difficult for single copy measurements, but if you have access to 2 copies, you can do a so-called swap test, which gives you the purity directly, and you can do it efficiently. And with this strategy, basically, we teamed up with Google and managed to come up with this plot where you can see an exponentially growing rigorous lower bound on the best performance of a standard prepare and measure scenario. The green dots are classical shadows, and the other lines beat it, and those are these quantum enhanced entangling 2-copy measurements where you can remain efficient even if the number of qubits goes up to 20. And I'm very proud because this is data taken from an actual quantum computer and one of the largest quantum computers in the world. And I think these experiments wouldn't have been possible without these efficient readout techniques that we started out with. And I think this is a good time to close. So thank you very much for your attention. Thank you for the many questions I got throughout the talk. Just as a reminder, we developed strategies on how to read out the relevant information of a quantum computer and how to do it efficiently, both in theory and in practice. Thank you.
So thank you very much for this very nice and lively presentation. It was also interesting for non-experts to hear it, like myself. Are there any questions? I guess a lot of questions have been asked during the talk.
Yes.
Do you have extra questions? Oh, yes. Yes, please.
Referring to the very last part of your talk, what do you mean by having 2 copies of the system available at the same time and doing correlation measurements? I mean, in what sense can the 2 copies of the system be correlated among each other?
Excellent question. Thank you for allowing me to clarify it. Envision that I have kind of like a classical quantum architecture with, let's say, n qubits that can prepare a certain system of interest. Think about a quantum quench or something. Then this is kind of like I can simulate this with an n qubit unitary on my n qubits, right? And let's assume this is efficient. Now suppose I have a twice as large quantum computer with 2 n qubits. I can run this evolution twice. First on the first n qubits and then on the second n qubits. And I end up with 2 copies of the final quantum state on the same quantum computer. Okay? And then the actual measurements we propose to get these exponential advantages are very simple Bell-type measurements between individual qubits. So I do a Bell basis measurement between the first qubit of the first copy and the first qubit of the second copy. And in parallel, I do a Bell basis measurement between the second qubit of the first copy and the second qubit of the second qubit. So this is a very efficient short circuit where I only jointly measure pairs of qubits, but it is maximally entangling because it's a Bell basis measurement, and it actually diagonalizes the swap operator. So obtaining the purity, or kind of purity becomes native in this setup. So this is now a quadratic measurement procedure where I can estimate the purity in a constant number of steps. Was this helpful?
Yes, we're running out of time unless there's another quick question. So let's thank the speaker again.